So welcome back in the class of microfilters. So in this class we're going to do one design example for a stepped impedance filter. In the previous class we have seen like how an inductor in certain approximation can be replaced with a high impedance line while the capacitor can be replaced with a transmission line with a low characteristic impedance line. So in this class we're going to do a design example. So the design example statement I'm reading for you. So we need to design a stepped impedance low pass filter having a maximally flat response and a cutoff frequency of 2.5 gigahertz. It is necessary to have more than 20 dB of isolation at 4 gigahertz, and the filter impedance the system impedance is given as 50 ohm, highest practical impedance is given as 120, and the lowest impedance is given as 20 ohm. So let's write down the key information for this example. So the first thing is choice of the filter. So we have a maximally flat response. Okay, this is the first thing. The second thing is given as the frequency, the cutoff frequency is given as 2.5. And the third parameter which is given as the PLR should be greater than 20 dB at frequency of 4 gigahertz. The fourth important thing which is given in this problem is the practical high impedance line could be designed for a value of 120 ohm, while the lowest characteristic impedance we can realize is 20 ohm. And we have also given the system impedance, or sometimes also known as R0, is given as 50 ohm. Okay. So the first step to solve this kind of problem, so we need to decide which is the order of the filter. So let's have a calculation for order. Okay, so we know that for a maximally flat, the PLR is given as 1 over k square omega upon omega c to the power 2n. Okay, where k is the proportionality constant. If we solve this equation for order, so we have found like the order can be calculated as 10 to the power PLR by 10 to minus 1 divided by twice of log 10 omega upon omega c. So while putting all these values, we can have some order, and this order can also be calculated graphically. So we have a procedure to calculate order graphically. So we have one equation, so one graph in our book which relates with two things, omega upon omega c minus 1, and here we have the PLR value. Okay, so and this has some sort of, okay, so here comes the filter order N1, say N2 and N3. If you closely observe, so this is say 1 and this is say 1.2 and something and so on and so on, and these values are less than 1. So if we closely observe for this case, we found that the filter order, when we are taking filter order as 5, we are exactly at the point where we are meeting this requirement of 20 dB. So we are exactly at 20 dB when filter order is equals to 5. So as the problem suggests, we need to have slightly greater insertion loss. So we need to choose the next higher order filter. So we have chosen n equals to 6 to have the PLR which is greater than 20 dB. Okay, so this can be easily seen in our book for like these graphs. So we have chosen filter order as 6. Okay, so let's design a low pass maximally flat filter for the order 6. So this filter would be have something like a capacitor, then an inductor, then another capacitor, then again an inductor, then again a capacitor. So how many elements? 1, 2, 3, 4, 5, and then one more inductor. So there are 6 elements. Okay, so this is gonna be G1, G2, G3, G4, G5, and G6. And we have given a system impedance, okay, as a 50 ohm, and here also as 50 ohm. So right now, as we are working in normalized domain, so let's put these values as 1, and here also these values as 1. We'll get back to the 50 ohm when we renormalize all the values. Okay, for maximally flat, so the first step, like calculating the order, so we have obtained the order as 6. The next step is to calculate the G parameters. So for G parameters, for maximally flat, we can calculate as G0, because which is given, G0 is the first element, which is equals to 1 normalized value. Similarly, the Gn plus 1, which is equals to G, order of the filter is 6, so this is going to be 7. This is also 1. So the rest G parameters, say Gk, the expression for Gk is given as twice of sine 2k minus 1 into pi divided by 2 into n. So we have seen like this expression, how this expression came in the previous classes. So we can solve for every k. So we need to put k equals to 1. So we'll get a G value for G1. So I'm just writing down all the values because it's really simple. So I'm just writing these values from the solution. So G1, so G1 comes out to be, after evaluating this, 0.517. G2 comes out to be 1.414, and G3 is 1.932. And we know that these filters, like we have a symmetry, so G3 going to be equals to G4, 1.932, and G5 is equivalent to G2, so 1.414, and G6 going to be same as G1, 517. Okay, so here we have the G parameters. Now the next step is to replace these G parameters into an equivalent stepped impedance line. Okay, so we have seen in previous configuration. So let's put as like the section number. Okay, so let's consider this as one section, the second section, so something like that. Okay, so the first section and the impedance, it could be ZH or Z low, and the electrical length, so beta Li. Okay, so the first element of this section is an capacitor. Okay, so is it a capacitor? In the formulation, we have seen a capacitor can be replaced with a low impedance line. So low impedance line is 20 ohm for us, or we can write as Z low if we want to design for some other low impedance line, like low impedance value. And then we need to calculate the beta Li for, say, how much is the electrical length for this capacitor. So we have seen in the expression, so this is expression for calculating the electrical length. So we have derived this relation in previous class, so we can refer that. So now if we calculate this, C is basically a normalized reactance. So C here can be written as C1, and C1 is equivalent to G1. So this can also be written as G1 ZL divided by R0, which can simply be written as G1 is 0.517, ZL we have 20, and R0 we have 50. So if we solve this, its value gonna become in radian, and we need to convert into the degrees. So this value comes out to be 11.8 degrees. Okay. Similarly for second element we have an inductor, and we have seen this inductor can be replaced by a high impedance line. So we have a choice of 120 ohm as our high impedance line and the electrical length for this high impedance line is calculated as LR0 divided by ZH. So we have derived these relations, you can refer these relations. So this is the second element. So this could be also written as G2 R0 divided by ZH. So G2 is 1.414 multiplied by 50 divided by high impedance, we have 220. So this comes out to be 33.7 degree. Okay. So similarly, we can calculate all the values for, so this again 20 ohm. Okay. So this gonna be C3, this is L2 ZL divided by R0. So if we say C3 is equals to G3, so 1.932 divided by multiplied by Z low is 20, and this is R0 as 50. So if we solve this value comes out to be 44.29 degree. Okay. So we have seen the symmetry in the problem. So the rest other values of electrical length. So this will become beta L4. This will also beta L5, and this will also equivalent to beta L6. Okay. So now we have almost all the things to design a stepped impedance filter. So how the final filter will look like. So we will see how is the final filter will look like. So we have a system impedance, which is Z0 equals to 50 ohm. Okay. Then we need to design a capacitor, which is a low impedance line. So based on the available space, I'm taking this as Z low, which is 20 ohm. Okay. Then again a high impedance line to represent this inductor. Then again a low impedance line to represent a capacitor. Then again a high impedance line to represent a inductor, and then capacitor. So 1, 2, 3, 4, 5, and the last line is as an inductor, and then we have again a system impedance of 50 ohm. Okay. So this section, so if we closely observe this section is our low pass filter. So it consists of 1, 2, 3, 4, 5, 6 elements. So the order of the filter is 6. So this impedance is Z low, and this is high impedance. This is going to be 120 ohm. this is going to be again 20 ohm, this is going to be 120 ohm, and so on and so forth. So the beta L is basically the electrical length of these lines. So this first line comes out to be 11.8 degrees. The second one is 33.7 degrees, and the third one comes out to be 44.29 degrees. And again we need to, for the symmetry, so this is 11.29, and this comes out to be 33.7 degrees, and this comes out to be 11.8 degrees. So this is how we can design a filter through stepped impedance transmission line. And if we have given the parameters for the substrate, say suppose if we choose a substrate to have a per epsilon value of 0.4 and 0.2, and if the 10 delta is given as 0.02 and the thickness of the substrate is given as 1.5, so we can practically realize these filters on a PCB technology. So the next step is to design a distributed filter design with this substrate parameters in a microstrip line, and you can put these transmission line with that equivalent electrical length and width with the transmission line formula, and try to see whether you are getting a low pass filter response something close to the cutoff frequency that we have designed. So this is your simulation exercise. You can simulate this problem in any simulators. So maybe I would suggest to go for ADS and simulate and see whether this filter is giving us a better isolation at 4 gigahertz, okay, more than 20 dB at 4 gigahertz, and its cutoff frequency is almost equals to the 2.5 gigahertz. So thank you.